back-to-back 2-hour classes. So I will see what to do, but yeah, at around 10 o'clock, in fact, we'll take a break for 5 or 10 minutes if you want to continue. I will try to still see if you have any discussion. Otherwise, I'll continue the class. Okay. All right. I have given these assignments. So I hope all of you have noted down. So what would be the due date for submitting this assignment this Thursday? Is this Thursday all right?
Okay, Thursday is all right, I
So
think.
because I have given on Friday, and this Thursday should be okay. And this Friday's class at 3 to 4 will be taken by Professor Sangita Sen. Okay, and then she will continue next week as well. Is that right, Sangita?
Yes, that's fine. And the assignment, I will open a portal on VLearn for submission. Okay.
Okay, no problem. All right, so let me share the screen now. And yeah, I mean, the last class, of course, we did the necessary matrix algebra. So I just thought I'll quickly revise as I normally do. So that essentially is a class of matrices, linear algebra. We did eigenvalue equation of matrices. In particular, we talked of Hermitian matrix, for which the eigenvectors can be made to be chosen to be orthonormal to each other, and the eigenvalues are chosen to be will be real. So we said that the same eigenvalue equation for an n by n matrix, which is n eigenvalue equation, can be recast as a single equation with a unitary matrix being formed out of the eigenvectors. So if you form a unitary matrix with the eigenvectors, the n eigenvectors in columns, then we can recast this as a AU equal to UD, where D is a diagonal matrix consisting of the eigenvalues. So that is something that I gave as the first example to show that the above U matrix is first unitary. And then, of course, the n eigenvalue equations can be written in this form. So that's the second part. So these are the A and B that I had given. So having done this, of course, it would essentially mean that you can do a unitary transformation of the A matrix such that the A matrix become diagonal. So that could be another way of looking at the eigenvalue equation, to find such a unitary transformation of this given matrix such that after the transformation, the matrix becomes diagonal. Okay, so it's important to note that for a Hermitian matrix, it is always possible to find such unitary transformation. Then we did something for function of a matrix, and we said if I have a function of a matrix, then you can first calculate the function of the first you diagonalize the matrix A, and then calculate the same function of the diagonal matrix and back transform. So do the unitary transformation, but in the reverse manner, where U will be on the left, U dagger will be on the right, so that the function of this matrix can be written as U function of the same diagonal matrix, U dagger. Okay, so that was one thing that we learned, and this is very useful to calculate, say, for example, A to the half, you can diagonalize. So first thing is to always diagonalize this. That's very important. And then have the same D to the half, which is very easy. Remember, the ease is that function of a diagonal matrix is very simple. So you just have to see what it is to be done, and that you do all the diagonal elements. So any D to the power half is essentially taking square root of the diagonal elements, and then you do a reverse transformation, you get A to the half. So I think that is a very important part to learn. Then we also talked about the resolution of identity over the full space. If you take Ket and Bra, sum over them, then you get an identity. And we also said that the identity matrix is, of course, an idempotent matrix. But more important, we said, if I do any projection over even an incomplete subspace, it's also idempotent. So it's as long as these are orthonormal. Of course, they are orthonormal eigenfunctions. So that's P squared equal to P. So these are called usually projection operator. and not necessarily identity, but identity is, of course, uh, a projection operator. Okay. So I think we just showed why it is projection, because it acts on an arbitrary function. It picks up the subspace of these phi i's, m dimensional subspace inside. So that's why it is called a projection. It is as if it is projecting out. All right. I remind you that we discussed on the 20% class test, 20% assignment. So one of them has been given, 30 NSEM, 30 MIDSEM. Okay. All right. So I think we'll go to the next part of today. And having introduced some amount of mathematics, of course, we did something different on that 3 to 4 p.m. class. So that I didn't revise now, but that I've done when I started the 6 o'clock class on Friday. So let me just now start today's class. Okay, so I will come back to the question and the problem that we are discussing about the many particle problem. And in particular, we will talk about the two particle problem. Remember, the two particle problem is just a model problem, but many of the understanding that we'll have is also applicable to particle number when it goes above 2. All right. I hope I'm audible, because today my internet is bad. There's a lot of fog in the campus. So I'm not very sure. Am I audible?
Yes, sir.
Yeah. Okay, good. All right. So we already learned the non-interacting theorem that if a Hamiltonian of a two particle or many particle is decomposed into sum of one particle Hamiltonians, then one can simply calculate the eigenfunctions and eigenvalues of the one particle problem, and then construct the n particle problem by a product of the set of the eigenfunctions, and the eigenvalue will be a sum. So that is what we said, multiplicably separable and additively separable. For electrons, of course, you have to remember that this product will have to be an antisymmetrized product. So essentially, that means we have to make sure that the total overall wave function is antisymmetric, okay, with respect to the interchange of the particle. So even if it is non-interacting or interacting, it doesn't matter. However, as you know, that most of the Hamiltonian are that we will discuss are not non-interacting. So exact solution is not possible. So we have to resort to approximate solution. So that was the whole context of this course that we discussed. So couple of approximate methods which are very, very popular we will discuss. One of them is called the variation method, which we'll discuss first, and another is called the perturbation theory, which we'll discuss a little bit later. So they will become the very important parts of this course. But let me first continue with the theme of these two particles. So if essentially I have a Hamiltonian which is 1, 2, and I have some wave function, psi 1, 2. I may or may not know this. But let's assume that I can write this wave function in terms of this simple concept of orbitals, which of course is possible exactly when this is non-interacting. Okay, but if it is interacting, we don't know still how to write the wave function. But let's assume that we still write the wave function in terms of the spin orbitals, with one of the electrons in spin orbital chi I, another electron in spin orbital chi j. Okay, so let's assume, look at this wave function. This can be exact wave function for a non-interacting Hamiltonian. As we have seen, it's a product. Of course, it has to be antisymmetric product. So that will come down to that. So, but let me analyze this product itself a little bit. So I have written down this product, chi I2, chi j1. So 1 by square root 2 factorial, if you remember the product. So in which case I have taken two one particle functions, chi I and chi j, and then made a combination. If these are eigenfunctions of the one particle Hamiltonian, and the two particle Hamiltonian is simply a sum of those two one particle Hamiltonian, then this is an exact wave function. But in many cases, this will not be exact, it will be approximate, because your Hamiltonian is not non-interacting. These functions can be arbitrary, so for various reasons, they will be an approximate function. But let me analyze the function first. As you know, the spin orbitals chi i's are are constructed out of a set of orbitals multiplied by alpha or beta. So I hope you remember that the number of spin orbital set is always twice the number of orbital. Now we have also seen that since this has to be antisymmetrized, the two spin orbitals chi I and chi j cannot be equal, as you can see clearly, because if I is equal to j, this term and this term becomes identical despite interchange, and the entire wave function becomes zero. So obviously this is not allowed. So we have to make sure that the spin orbitals are different, and this is also the content of the Pauli exclusion principle. I must also say that such a antisymmetric wave function consisting of two orbitals can be written in a more, I would say, in a way which can be easily extended to larger number of particles. And that is what was introduced by Slater in the form of Slater determinant. So first I want to tell you that please do not worry if this wave function is exact or not at this point of time. As I told you, it will be exact in certain case if the Hamiltonian is a sum of two one particle Hamiltonians, and these are the eigenfunctions of that Hamiltonian. So then in that case it will be exact. But assuming that I write any wave function of this form, it is a valid wave function. It may be an approximate wave function, but it's a valid wave function because it satisfies the symmetry properties. If something does not satisfy symmetry property, it's not even a valid wave function. But then it's an antisymmetric wave function, so there is no problem. What I'm trying to do is to write such antisymmetric wave function in terms of a determinant, and there are a couple of ways of doing that. But let me first write this as a determinant, as all of you know. The determinant will have a rho which will be determined by the coordinate of the electron. So let's say coordinate 1. So as you know, determinant has rows and column. And column will be determined by the orbital, a spin orbital. So please try to see how we have written the determinant. I have two basic variables. One is chi1, chi I and chi j. So I can call this, let's say, chi I. Let me call this chi j, just to be consistent with this function. So this is the column of chi j. This is the column of chi I. This is the row index is of the electron coordinate 1. And so first row is column 1, electron coordinate 1. Second row is the coordinate 2. So I hope you can write this. Of course, you may choose to write by interchanging row and column. So for example, if you write this as chi I of 1, chi I of 2, chi j of 1, chi j of 2. So just carefully see these two determinants. Instead of column I have made the spin orbital in the row and the coordinates in the column. Okay, is there any question? Please ask me. If you expand these two determinants, you can see the result is identical. It still has chi I1, chi j2 minus chi j1, chi I2. So exactly the same, right? So you have a choice. I am using this notation because in the text of Szabo and Aslund, if I remember, this notation has been used. But please remember that this can be interchanged. So there is nothing hard and fast that you have to use the column, or spin orbital in the column and coordinates in the row. There is nothing like that. You can interchange this. In any case, so I will continue to use this as the building block. So if you look at this determinant and multiply by 1 by square root 2, I will justify the 1 by square root 2 a little bit later in terms of normalization. You see that this or this is actually representing this. I hope it's very clear. This is simpler to write because I don't have to bother. I have a very simple recipe of extending to n electrons and n spin orbitals. Because in Pauli principle, or for electrons, we know that all spin orbitals have to be different for n electrons. So if I have n electrons and n spin orbitals, I can still write an extension of this determinant very easily. So that is why I'm saying that the determinant is a convenient form. The determinant also shows why if I interchange coordinate electron 1 and 2, or spin orbitals I and j, it will be antisymmetric, because this means I'm flipping the two rows or flipping the two columns, right? And all of you know that the determinant changes sign if I interchange two rows or two columns. Is that right? So obviously, this determinant is antisymmetric. So it's a very nice way to write this. And Slater actually introduced this. And this kind of way of writing are called Slater Determinant. So that is something that you have to learn. So let's assume that I have n electrons and n spin orbitals. For all, so now I'm explicitly talking of electron. Remember, for boson, it's completely different because it has to be symmetric, so it can't be a determinant for bosonic systems. So I have n electrons in n spin orbitals. So this is going to become 1 by square root n factorial. Again, this I'm just introducing, and I'll justify this factor, but don't worry about this factor because it's just a multiplication number. So I have chi1 1, chi2 1, etc. up to chi n 1. Then chi1 2, chi n 2. I hope you can see how to write it. And then the coordinate 3 will come, and eventually coordinate n will come, chi1 n, chi2 n, chi n n. So you can see that the first row becomes the coordinate electron, second row coordinate electron 2, and coordinate electron n. First column is chi1, second column is chi2, and so on. Nth column is chi n. So it's very easy, and I'm using this notation. Of course, as I told, you can interchange row and column. Perfectly okay. Do not worry about this yet. You can now see that it is antisymmetric. Because very fact that I have a determinant, it's antisymmetric. If you can expand, the first term will be leading term will be this diagonal, and then of course you can keep on expanding. But you can see it's extremely difficult to expand like this without understanding. Here it was easy because I know that this is not symmetric. I could antisymmetrize by manually. But for n electron, n spin orbitals, it would have been impossible. But the determinant gives you a natural way of writing an antisymmetric wave function. So I can say that antisymmetric wave functions are note here, if I had two determinants, not one. For example, one determinant with chi I, chi j, another determinant with chi k, chi l for a 2 electron, and I just take a linear combination, that is also a valid wave function because each determinant is antisymmetric. Of course, you will ask, why would I take two determinants? The answer is you already know that I told there are many cases where one of these determinant is not exact because the electrons are interacting. So for example, if I write a wave function, two electron wave function as C1 into a determinant 1 by square root 2 chi I1, sorry, chi J2, chi J1, chi I2, chi J2 plus C2 1 by square root 2 chi K1, chi L1, chi K2, chi L2. If I write a determinant like this is also a valid wave function. Right? Of course, chemical interpretation of this wave function, this is a mathematical description. Chemical interpretation is very difficult because when there is only one determinant, I can always chemically interpret as two electrons in two spin orbitals. But now I'm saying, yes, two electrons are there, but they are in Ij, they are in KL. There could have been Ik. IL, all kinds of combination. I've just written two combinations. So the chemical interpretation is very difficult for such a wave function, but mathematically, such a wave function is a valid wave function because each of them is antisymmetric. So the sum is also antisymmetric. Okay? And many cases, we may require such a wave function because either of these determinants may not be the exact simply because the Hamiltonian is non-interacting. So as you know, if Hamiltonian is non-interacting, we cannot write because the Hamiltonian is, not non-interacting. Hamiltonian is an interacting Hamiltonian. So the Hamiltonian is an interacting Hamiltonian. I cannot write by either of them, may not be right. But then we can try a combination. So there are several possibilities that we can do, and we will see how to do that. Okay, a little bit later. But I'm just at this point, I'm telling that if I write a combination of two determinants, combination of three determinants, this is an example. That's a valid wave function in terms of antisymmetry. Okay, and we will require this as we go forward, simply because our Hamiltonian is not so simple Hamiltonian. If a Hamiltonian is simple, one such determinant properly chosen, with the spin orbitals being the eigenfunctions of the one particle Hamiltonian, would have served the purpose. But since that is not true, I just wanted to tell you this. All right, so let me now go back to this determinant of two electron determinant and first justify this 1 by square root 2. Okay, so let me say if I have a determinant like this, chi I1, chi J1, chi I2, chi J2, and I don't know what is this constant. So what I will do, I will first take the conjugate of this and multiply and see if I integrate what I will get. So I have to integrate these two determinants. So chi I star 1, chi J star 2, chi J star 2 minus chi I star 2, chi J star 1 into chi I1, chi J2 minus chi I2, chi J1. So I'm just basically trying to find out the normalization. So I'm doing psi star psi and integrating over the two volume elements, deta 1, deta 2. So we have to see what will happen now. Okay. So I will first take this term and this term. If you know, there are four terms, this with this, this with this, this with this, this with this. There are four terms. So if you take up this term, it is chi I star 1, chi I1, chi J star 2, chi J2, deta 1, deta 2. Quite clearly, all spin orbitals are orthonormal. So that's the only assumption that I have done, that the one particle function that are chosen are orthonormal set, which is, of course, without any loss of generality, we can do that. So that means the first term is 1. I hope all of you can see that. If I integrate between these two terms, then I have a chi I star 1, but I have a chi J1. So when I do chi I star 1, chi J1, deta 1, it is 0. And of course, similarly, chi J star 2, chi I2, deta 2 is also 0 because I and J are orthonormal. I and J cannot be anyway equal. You know that. And the same thing applies for this cross term. However, when I take these two terms, you can see again chi I star 2, chi I2 integrates to 1, chi J star 1, chi J1 integrates to 1. So the answer of this integration is actually 2. 1 here, rest are 0. Is it clear to all of you? This integration,
Yes,
is it clear?
yes,
There
sir.
are four terms I've
Yes, sir.
integrated over coordinate 1, coordinate 2, and because of the orthonormality, the result is 2. Hence, the normalization constant is 1 by 2 factorial. Is it clear?
Yes, sir.
Okay, good. When I go to n by n determinant, now I can argue in the same manner. First of all, as understand that is not 1 by square root n, it becomes n factorial, which is actually true for 2. In the 2, I didn't realize whether it's 2 factorial or 2 because the results are identical. Okay. So when I come to n, please state that I have to expand this. And the expansion is very complicated. But important to realize I will have n factorial terms. Not n terms. I will have n factorial terms in the left, n factorial terms in the right. So when I do the integration, there will be n factorial terms here, and there will be n factorial terms here, plus, 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 etc. Now, exactly in this manner, what happened here? Only when the terms exactly matched on the left and the right, it survived. Any change, it is 0 because of orthonormality. So you can see now, each term to each term will only survive. Any cross is 0. So this, let's say this is term 1 conjugate, this is term 1 here. This is term 2, this is term 2 here. So you can clearly see 1 will survive with 1, 2 will survive with 2, 3 will survive with 3. So 1, 2, 3 up to n factorial are basically the expansion, some way of expansion. So one of them would be, let's say, this is, let's say, chi1, chi1, chi2, 2, etc., etc., chi n. This is the term 1. The term 2 could be 1 interchange. Say chi1, 2, chi2, 1, the rest remains same. Chi3, 3, chi n. So all n factorial permutations will actually be n factorial term. But the important thing is that one term with one term will not survive. So how many survivals are there? N factorial. Am I right? 1 with 1, 2 with 2, 3 with 3, n factorial with n factorial survive. Number of terms. These are the number of terms. So if it is 3, n is 3, there are 6 terms here. There will be 6 terms here. So the result will be 6. Is it clear? So the result of the integration will be n factorial. Hello? Hello?
Yes, sir.
Yeah?
Yes.
So the normalization constant will then become 1 by n factorial, square root. 1 by square root n factorial. So I hope you now understand why we are writing this. This is just to normalize because of the several terms that appear and the fact that the spin orbitals are orthonormal. So the normalization constant is 1 by square root n factorial. So every time we write a n by n determinant, there is a normalization 1 by square root n factorial. So I again repeat this. So if I have a chi1 1, chi2 1, chi n 1, chi1 2, chi2 2, chi n 2, and so on. Every time I write this, there has to be a 1 by square root n factorial for normalization. If you want to normalize, but then, as all of you know, that's not very important thing. Okay, it's just a normalization constant for this determinant. So, but you have to normalize. So it's 1 by square root n factorial, which is something that you will remember. I hope that every time it is there. Since every time it is there, it is very cumbersome to write a determinant. Often we'll use a simpler symbol to note this determinant. So the symbol will be simplified. What we will do is the following, that we will write within the bracket only the list of n spin orbitals, okay, or just the diagonal term very often. So we can even write simply chi1, chi2, chi n. That's all that is required. And you should be able to know the determinant. I hope that's clear, because what is important is not even coordinate 1, coordinate 2, coordinate n. I could have said 2, 3, 4, n plus 1. What is actually important is what spin orbital I'm using, because chi1, chi2 are forms of functions. So those functions have to be specified. As long as I have specified this, I actually have specified this. So many times I'm going to use simply chi1 to chi n, or if I write chi1 1, chi2 2, chi n, you should know that I have written the leading term of the determinant, which is the diagonal term, and the rest is automatically there. But then I'm suggesting that writing 1 to n is also superfluous because it doesn't matter. What is important is just the spin orbitals. So very often I'm going to write only this, and it will also assume, if I write, that you have a 1 by square root n factorial. So what I'm now suggesting is that the entire determinant 1 by square root n factorial, chi1 1, chi2 1, up to chi n 1, chi1 2, chi2 2, up to chi n 2, and so on. Chi1 n, chi2 n, up to chi n n will be written as chi1, chi2, chi n. Just 1 minute. There's a phone call. I'll pick up and come back. ক্লাস হচ্ছে না কি এত কিসের প্রবলেম হচ্ছে আর পাবলিকেশন লাগবে না পুরো পুরো পাবলিকেশন লাগবে না ঠিক আছে আমি আমার ক্লাস হয়ে যাক আমার ব্যস্ত আছে আমি বিকেলে আগে দিব ওকে বাই হ্যাঁ বাই Hello?
Yes, sir.
Yeah. All right. So this entire thing would be simply written in this form. I hope it's clear. I mean, many times I will write the full form, but what I'm saying is that if I write the abbreviation, it should be very clear that this expands into this, because it is much simpler to write. So if I write chi1, chi2, it's very simple. What I want to say, that 2 electrons in 2 spin orbitals and then antisymmetrize. How to antisymmetrize, I will not worry, because you know how to do that with the row and column. So please let me know. This is a new thing that you are doing. Those who have not done Slater determinant, it's very easy. So if I say, let's say hydrogen molecule, you have done hydrogen molecule, I would say that one of the electrons is in sigma g with alpha, one other electron with sigma g with beta, right? So that's the very standard convention of the 2 electrons in sigma g orbital. So I'm talking of spin orbital. Remember, however, when you write determinant, it must be in terms of spin orbitals. It makes no sense to write a determinant in terms of spatial orbitals alone. So you have a sigma g alpha and sigma g beta, right? So all I will say is sigma g alpha, sigma g beta. It should be clear. All right. If I write another orbital, that means I've excited the hydrogen molecule. So for helium atom, for example, ground state, I can write 1s alpha, 1s beta. So these are very simple way of writing and abbreviating what we are trying to do. And this will not only be expanded in a determinant form, assume, but also assume that I have the normalization constant. So they are normalized. Of course, it also assumes that the spin orbital themselves are normalized, which they are. Okay, to start with. In fact, we very rarely start with a basis function or a set of functions which are non-orthonormal. We never do that. All right, so with some of these technical things are very, very important. I come back now to a somewhat different discussion. So let us say that I have the 2 electron wave function. Now let's not worry if that wave function, as I said, is exact or approximate. It will be exact under certain conditions only. Otherwise, it will be an approximate wave function. But let me come back to the discussion that I have a psi I 1, 2, and they are chi I, chi j. So I think I am very clear now what I'm trying to tell you, that these are the two spin orbitals, which are, one of them is chi I, one of them is chi j. And you can write in determinant form. Okay. And then I say that my chi I is some orbital phi 1 with the alpha spin, and the chi j is the same orbital or some other orbital with a beta spin. So it can be phi 1, it can be phi 2. So I'm assuming it, for generality, some other phi 2. So the space orbitals are also different, spins are also different. So I'm just taking an example. So let me now see what happens to the probability of finding the two electrons, the probability density of finding the two electrons at a spatial coordinates R1 and R2. Because remember, when I'm writing this determinant, they have the coordinates are now no longer spatial, they are R omega. So can I do R1, R2, which are basically the two electron coordinates, when one of the spin orbitals is phi 1 alpha, another spin orbital is phi 2 beta. So I will now expand the spin orbitals. So since I'm doing something new, I have to write this as a 1 by square root 2 phi 1 1 alpha 1. So that is chi I 1, phi 2 1, sorry, phi 2 2 beta 2, right? So that's the first function. So I'm taking this as this. Then another 1 by square root 2. So this will actually become 1 by 2. This is conjugate. And then I have exactly the same thing. Phi 1 1, alpha 1, phi 2 2, beta 2. So if I write this manner, then of course, this is going to be basically the norm of the chi I, chi j. But what I want is a probability density at R1 and R2. So how will I do this? I will only take mod psi square. I will not integrate, right? So if I integrate mod psi square, then over the entire volume element, it becomes a norm. But if I want to take only probability density, what do I do in Born interpretation? Simply stop at mod psi square. But now the problem is, now my mod psi square is a function of R1 omega 1, R2 omega 2, because it has spin orbital. I want only the probability at a spatial points R1 and R2. So what will I do here? I will integrate over the spins of the 1 and 2 only, not the whole integration. So I have to write a custom writing. So let me write now probability of R1, R2. So let me go through very slowly. I have half, I have 2 and 2 4 terms, right? So there is a minus this thing. There is a minus, sorry, this is a minus this thing. So I have 2 and 2 terms. Here there is an exchange term, here there is an exchange term. So I will write the exchange term here first. So remember my determinant, chi I 1, chi j 2 minus chi I 2, chi j 1. So I am now writing this the left hand side. So you have a phi 1, 1, alpha 1, phi 2, 2, beta 2, minus phi 2, 1, beta 1, phi 1, 2, alpha 2. I hope it's clear. And there will be 1 by square root 2 coming from left and right. I have merged it together. I will do the integration a little later. So this is my one term. Into, I take the same term again, mod psi square, right? But this is conjugate. So this if you want, I can write all star, but I hope it's clear. The left side is the conjugate. The right side, I'm going to write again the same term, phi 1, 1, alpha 1, minus phi 2, 2, beta 2. Phi 2, 2, beta 2, minus phi 2, 1, beta 1, phi 1, 2, alpha 2. And then I integrate over d omega 1, d omega 2. So plus try to understand what I've done. I have taken psi star, I have taken psi. I'm integrating over only the coordinates of electron 1 and 2. So what I will get is a probability density involving the electrons' spatial coordinates R1 and R2. Is it clear to all? So once I'm able to write this, doing the integration would be trivial. That I will see how to do it. But so what I have written is basically integral psi star psi. So what I have written is the following: integral psi star psi d omega 1 d omega 2. That's all. Where psi is a 2 electron determinant. Phi 1, phi 2. They are the orbitals, space orbitals, and the spin orbitals are alpha, beta. I have taken a very general chi I and chi j. Okay, but important thing is that one of them is alpha spin, one of them is a beta spin. That is important, remember. So I have taken a determinant of 2 electrons which have alpha beta spin, and I'm first doing this as an example. So, but this part that I'm doing is very general. This specifically alpha and beta are written here. Now when I integrate this, how will I integrate? Exactly the same idea. Integrate the 4 terms, this with this, this with this, this with this, this with this. I hope it's clear to all of you. So the first term is, an integration is only over coordinates of 1. That means phi star phi will not be integrated. They will remain. It's only alpha star alpha 1 over d omega 1. That's 1, right? Alpha is normalized. Correct? Beta star 2, beta 2, 1. So only what will remain is phi 1 star 1, phi 2 star phi 2. Phi 1 star phi 1, phi 2 star phi 2. Once I go from here to this term, then alpha 1, beta 1 will become 0. Beta 2, alpha 2 will also become 0. So it will not survive because of spin. I do the same thing, exactly the same thing will happen. Cross will not survive. This will survive with this. So if I now write this, what remains is the following. Half equal to half of what remains is phi 1 star 1, phi 2 star 1, phi 2 star 2, phi 1 star 2. So what remains is the phi 1 star 1 for the first term. So I'm writing the first term with the first term. So phi 1 star 1, phi 1, phi 1, 1. So it is the electron 1 in this spin orbital 1, a orbital 1. Phi 2 star 2, phi 2, 2. It's a density P R1 R2. So there is no integration over R1 and R2. I'm just writing. Okay. And then I have similarly just this term surviving, which is phi 2 star 1, phi 2, 1, phi 1 star 2, phi 1, 2. So plus phi 2 star 1. So it's an interchange. Phi 2 star 1, phi 2, 1. Sorry, phi 1 star 2, phi 1. So that will be your PR1 R2. So you can see my PR1 R2 is very simple. The density of phi 1, the density of phi 2 multiplied twice. Because of the fact that the once electron 1 can be in phi 1, another time electron 2 can be in phi 1, and vice versa. With the half factor, of course, it will become mod phi 1 square into mod phi 2 square. 1 and 2. So I can write this as a half. More clearly, I will write this as a mod phi 1 square, sorry, mod phi 1 square 1, mod phi 2 square 2, plus mod phi 1 square 2, mod phi 2 square 1. Just to emphasize that the density of the electron 1, density of electron 2, and their interchange. And this is, of course, understandable because electron 1 and 2 are interchangeable. So when I said right in the beginning that this is my function, I don't know which is electron 1, which is electron 2, apart from the alpha beta. Now alpha betas are gone anyway. So electron 1 can be in phi 1, electron 2 can be in phi 2, or vice versa. And that is actually reflected here with the density. So I have the two densities, and that's why there's a factor half also. So everything looks very nice. And There is no further integration. Here, integration is already done. Okay, I hope all of you are able to follow this. Integration over omega 1, omega 2 is done, not over R1. So probability of two electrons being found at R1 and R2 will simply depend on these densities at R1 and R2 multiplied in the reverse order. Okay. Let me now take an example of the two electrons not antiparallel, but the two electrons which are parallel in any spin orbital. Of course, it has to be different spin orbital. So now I'm taking an example of chi I is phi 1 alpha, chi j is phi 2 alpha. So it's a case of a two electrons with parallel. It's very important to understand the spin part. Even though my wave function is approximate, it doesn't matter at this point. But I'm trying to understand what are the physical aspects which differ when the electrons are antiparallel, electrons are parallel. Okay. So as soon as I do that, I can now do the same example here. But remember, now everything is alpha. If everything is alpha, first thing to understand that not only these two terms will survive, this and this will survive, everything is alpha. So this with this will survive, this will survive. But even the cross terms, like this with this will also survive because everything is alpha. Is it clear? Why did the cross term vanish? That is, this with this vanished because this was alpha star 1, this was beta 1. Right? So that becomes 0. But if everything is alpha, it will all survive. All the four terms will survive. Can you see that? Hello?
Yes, sir. Pass.
I'm only integrating the spin. Remember. So all four terms will survive, which means I will have a phi 1 square, mod phi 1 square into mod phi 2 square 2, and whatever I wrote there. But apart from there, I will have a phi 1 star 1, phi 2 1, phi 2 star 2, phi 1 2. That will also survive. And similarly, phi 2 star 1, phi 1 1, phi 1 star 2, phi 2 2. I hope you can see that. So I will now write the probability in this case directly. If you have any discomfort with integration, please let me know. In this case, it was very simple like this. Electron 1 in phi 1, electron 2 in phi 2. Electron 2 in phi 1 or electron 1 in phi 2. That's all. But it is the density of the corresponding two electrons which are multiplied and sum. Okay? So average of these two was taken. But now you see the fun. Of course, this will be there. So let me write it down. Half. So let me write this, whatever is already there, phi 1 mod square plus phi 1 2 mod square. But in addition to this, there will be two more terms. So one will be this with this, which is a negative sign now. Phi 1 star 1, phi 2 1, phi 2 star 2, phi 1 2. Let me write it down. So minus phi 1 star 1. So let me again go back and see. Phi 1 star 1, phi 2 1. Not phi 1 star 1, phi 1 1. So phi 1 star 1, phi 2 1. And then phi 2 star, see here again, phi 2 star 2, phi 1 2. Right? So now the electron coordinate 2, phi 2 star 1, phi 1 2. Okay? If you look at the other term, which is this into this, it's exactly the same. Phi 2 star 2, 1, phi 1 1, phi 1 star 2, phi 2 2. So I can just write the exchange part in this manner. Phi 2 star 1, phi 1 1, but it's otherwise the same. Phi 1 star 2, phi 2 2. So provided these spin orbitals are real, these two terms are exactly the same. So this together is my probability. for a situation where the electrons are 2 alpha spin and they're in some orbital phi 1 and phi 2. Of course, we know if both electrons are alpha spin, the spin orbitals should be different. Phi 1 and phi 2 must be different. Though in the first case, it was not so, because phi 1 and phi 2 could have been same, because the spins are already different. So that will make the spin orbitals different. But I have taken a more general case. Now, if I compare this with this, if you look at this is basically a product of 2 electron density, one in phi 1, one in phi 2, which is what I don't know. That's why I have taken the average. But in this case, that is already there. In addition, I have a term which I cannot explain classically, because there is no density here. Look at the electron 1. It is phi 1 star 1 into phi 2. Sorry, this is 2. Yeah, this is 2. So I have a phi 1 star 1, phi 2 1. I have a phi 2 star 2, phi 1 2, which had no meaning. And same thing happens here. Phi 2 star 1, phi 1 1, phi 1 star 2, phi 2 2. So whenever you have a phi 1 star phi 2 for a coordinate 1, it is not density. Density is phi 1 star phi 1. I hope all of you remember the Born interpretation. Whatever is the orbital, square of it with itself. A conjugate of that with itself. But no, it is not so. I hope you can understand what I'm saying. This part has a very nice classical interpretation. And these parts which I got here, as well as here, are what are called the Coulomb interaction. Why it's a Coulomb? Because you have an orbital phi 1, you have an orbital phi 2, and I'm very simply saying there's electron 1 here, electron 2 here, they're interacting. Their densities are interacting. Okay? Except that this can be 2, this can be 1. That's a different matter, because electrons are indistinguishable. But this has a very nice interpretation, the first 2 terms, which was the same interpretation here. And that is a Coulomb interaction. So that is called the Coulomb interaction. So this probability comes out of a Coulomb term. You can say in a very simple manner, the 2 densities simply multiply. But in this case, this concept of density is not there. And there is no classical interpretation. So the first 2 terms in the probability arise out of Coulomb. The next 2 terms, the last 2 terms, can be actually called arising out of some effect, which are now calling it exchange. So it's very important to realize this Coulomb and exchange. This exchange, which probably for the first time we are seeing, is an artifact of the fact that the wave function was antisymmetrized right in the beginning. I hope you remember. Because it was antisymmetrized, I had to write these 2 terms. If it was not antisymmetrized, I would have written only 1 term. Factor half would not have been there. It's a simply Coulomb. So the exchange is coming. Exchange is a purely quantum effect, and it arising out of the antisymmetry. Antisymmetry of the electron. So this is basically what we call that any exchange, interaction, or any effect of exchange is a quantum effect. It cannot be just explained classically. Is it clear?
So can I ask a question?
Yes,
sir?
yes.
Here
Yes,
the first I choose 2 wave function is antisymmetric, and spin also antisymmetric.
What do you mean by spin? No. Antisymmetry is never done by spin and space separately. Antisymmetry is always with respect to the spin orbital.
Oh.
So,
And
yeah, so let me again recast. When I wrote this, it means the entire thing is antisymmetric. So that is the reason if you look, I have written phi star alpha 1, phi 1 star alpha 1, phi 2 star beta 2 minus phi 2 star beta 1, phi 1 star alpha 2. So when it is 1, it is coming 1 everywhere. 2, both of them are 2. Because this is together is going. So my spin orbitals are phi 1 alpha and phi 2 beta. In this case, phi 1 alpha and phi 2 beta. Yes, now tell me.
So when I integrate, both spin coordinates are same. So that means.
Yeah, both spin coordinates are same, but alpha and beta are orthonormal, right? So alpha
but
alpha
in
is 1.
So, but in general, they are not same.
Why? What do you mean by that?
মানে
No, the wave
first
function has both. Both wave function has 1 and 2.
Here, yes, that
I'm
I
only
understand.
integrating psi star psi. So when I'm integrating psi star psi, there will be a possibility, there has to be coordinates same, right? So I don't understand this. For example, take a simple 1 electron case. Forget about 2 electron. So 1 electron, let's say my spin orbital is phi 1 alpha. How will I integrate this function? So this is, let's say, chi 1, right? So I'm now calculating chi 1 star chi 1. Integrating over d omega 1. Only spin I am integrating. How will I do? I will write this as a phi 1 star alpha, phi 1 star 1, alpha 1. Chi again, I will write alpha star 1, sorry. Phi 1 1, alpha 1, and d omega 1. Whenever I am doing psi star psi, one orbital, the coordinates are same. Why is that confusion coming now? Whether it is spin or space, how does it matter? When I did, let's say I'm doing 1s star 1, 1s1. Is it not the same? When I'm normalizing.
Same.
So same thing will happen in spin. This is a completely different thing. It does not mean the electron 1 and 2 are in the same spin. Okay? That is a completely different matter. They will be in the same spin provided the orbitals are different. Because the entire spin orbital goes together. So when I'm doing this integration, how do you write? You write this one. And now I integrate alpha star alpha d omega is 1. So the same thing can be written as simply spatial orbitals. Phi 1 star r1, phi 1 r1, dr1. Right? If both of them have alpha spin. If both of them have beta spin, of course it will become 0. But now you know, if I want to antisymmetrize, this is not possible for alpha spin. So this I have to take phi 2. Because this is not a valid wave function. In a 2 electron case. But in 1 electron case, when I'm integrating, there is no problem. It's a density.
Okay.
So here also, for a 2 electron case, I have taken, that's why I have taken the antisymmetric determinant. So there are 2 terms here, But when I'm integrating one term with one term, then of course this will have 1 and 1. This will have 2 and 2. That's correct. There is no problem.
So the first one is alpha 1, second was of absolutely alpha and maybe beta 1. That's not matter.
Which one? No. The first one, this one is alpha 1. This is beta 2. This integrates with alpha 1 and beta 2. So the alpha 1 is 1, beta 2 is 1. So what remains is phi 1 star 1, phi 1, phi 2 star 2, phi 2.
Okay.
That I'm not integrating. Right? The same thing happens with this and this term. Beta star 1, beta is 1, alpha star 2, alpha 2 is 1. What remains is phi 2 star phi 2, phi 1 star phi 1.
Okay.
If I want to integrate this term with this term, that becomes 0. Okay. Is it clear to all?
Okay, sir.
So, but what is important to understand is the physical effect. When I have 2 electrons in an anti-parallel situation, alpha and beta, the space orbitals can be same, may not be same. Because antisymmetry can be done only with the spin. Because of the spin, antisymmetric wave function can be constructed. But I have taken general case of phi 1 and phi 2. What is important to realize that in the case of an anti-parallel spin, when I take a determinant, I have only Coulomb term. When I'm taking parallel spins, I have actually 4 terms. Coulomb as well as exchange. I think that is the most important thing that I want to tell. In terms of the probability density of R1 and R2. So distinguish the parallel and anti-parallel spin. That the parallel spins give rise to exchange. And this particular line will keep coming. Anti-parallel spin does not give exchange. It only gives Coulomb. When I take a determinant, I'm again repeating. So my wave function is one determinant. And I'm trying to calculate the probability of R1 and R2. In fact, I can calculate many other things, even energy. The same thing will come up. And I will show you later, because right now we don't know how to calculate energy, so I'm just showing you psi star psi. The important thing to understand is that the parallel spin gives you both Coulomb plus exchange. Remember, exchange comes with a negative sign, but effects are both. Whereas if I anti-parallel spin, I have only Coulomb. This is a very important part. Coulomb and exchange in terms of the space orbitals. After integration of spin. After integration of spin, in the probability, what turns out in terms of space orbitals is that both Coulomb and exchange survive. For the anti-parallel spin, only Coulomb survive, because exchange becomes 0 simply because the exchange comes out of that antisymmetric part where the spins are different, and the spins becomes orthogonal to each other, so it becomes 0. Is it clear? The physical effect. So for an anti-parallel spin, the exchange term vanishes. Due to spin orthogonality, which means alpha with beta is 0. Okay, I mean, this is a very, very important part. I think what I did, you should be able to do. Since I have 2 hour and 1 hour discussion, I will repeat this part by taking another example. Okay, so let me again restate what I did if the integration is not clear. So I have taken 2 spin orbitals, chi y as phi 1 alpha, chi j as phi 2 beta. So that's the first case of anti-parallel spin, where only Coulomb survive. So my wave function then becomes, it's an antisymmetric wave function, 1 by square root 2, phi 1 1, alpha 1. Please tell me if anything is a problem. Phi 2 2, beta 2, minus phi 1 2, alpha 2, phi 2 1, beta 1. You must be able to write this effortlessly. Can all of you write this effortlessly? Because I have a chi I 1, chi j 2, chi j 1. That is what I've written here, chi I 2. So when I'm saying chi I 2, both space and spin must be 2. Right? Then what I'm doing is the following. I'm integrating psi 1 2 star, psi 1 2, d omega 1, d omega 2. And I'm defining this as the probability density of 2 electrons at R1 and R2. I hope that is first very clear. Because in the Bond interpretation, psi star psi is a probability density. But this at spin, if I integrate spin, it becomes probability density only in space orbitals, R1 and R2. Is it clear? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. And this is what I call probability. So in this case of the anti-parallel spin, I showed, now you have to integrate this. This is a technical matter. I hope all of you should be able to do. 2 terms here, 2 terms here. So in principle, there are 4 terms, right? So this with itself, this with itself, this with this, this with this. I mean, one complex conjugate, it doesn't matter. Psi 1 2 star. But the important thing is that because alpha 1 star with beta star 1 would be 0 and vice versa, you can see that in such a case where there is an alpha and beta, it's very easy to show that the PR12 would only be half mod phi 1 square 1 mod phi 2 square 2 plus mod phi 1 square 2 mod phi 2 square 1. That is what I'm trying to say. Okay? I mean, I hope the integration is trivial to all. So I will take one integration, one side integration. So half integral. So I will take one of them. Let's say this with itself. So integral phi 1 star 1 alpha star 1. So I'm taking psi 1 2 star 1 term. Phi 2 star 2 beta 2. So I have taken one term of psi 1 2 star. Now I will take the same term with psi 1 2. So phi 1 1. Now no conjugate. Alpha 1 phi 2 2 beta 2. It's easy to see this. D omega 1. So one term I'm just writing. This is basically term 1 to term 1. I think this is a very simple definition. That means conjugate side term 1, there are two terms here, right? Conjugate time term 1, the right side also term 1. It is very clear to see it survives because alpha star alpha is 1, beta star beta is 1. So it just gives you mod phi 1 square into mod phi 2 square. Is it clear? Is it clear? Please tell me.
Yes, sir.
I'm integrating omega 1, omega 2. So only this survives, right? The same is true for term 2 to term 2. I don't have to show this. Of course, there will be a factor half. Sorry, I missed the factor. And that will give me half phi 2 square 1. That's the only difference that will happen. Phi 1 square, right? For the term 2 to term 2. That means take this term with itself. So only that 1 has become 2 here, 2 has become 1 here. Is it clear? So what I want to tell you that if I take a term 1 and term 2 or vice versa, T2 and T1, it will become 0. So to see this, you can take up this term. So again, half is there, half you forget. So I'm taking the term 1, which is phi 1 star 1, alpha star 1, phi 2 star 2, beta star 2. So let me write this. So phi 1 star 1, alpha star 1, phi 2 star 2, beta star 2. That is 1. Then I take term 2 on the right side with a minus sign. So term 2 on the right side, which is phi 1 2, alpha 2, phi 2 1, beta 1, right? And now I integrate with a negative. This is a minus sign. That's okay. D omega 1, D omega 2. Now you see the result. Alpha star 1 cannot be integrated with alpha 2, right? Alpha star 1 has to be integrated with the beta 1. And beta star 2 has to be integrated with alpha 2. They are all product. Right? There is no plus minus sign here. So automatically when I integrate, this will become 0. Is it clear? And so
Yes,
is
sir.
true for T2, T1. So that means the probability of R1 and R2 are just this term, this and this sum, which is the Coulomb term. Is it clear? Okay? If you turn this problem with a parallel spin, now if I take this thing with a parallel spin, not this, so let's say phi 1 alpha, phi 2 alpha. Then what will happen? All the 4 terms will survive. Because everything is alpha, there is no beta. So the fact that this term 1 and term 2 did not survive was because of this integration of alpha beta. But now if these are all alphas, just turn this around, everything is alpha, then everything will survive. Except that this part will become phi 1 star 1, phi 1 2, or phi 1 star 1, phi 2 1, phi 2 star 2, phi 1 2, which is not the Coulomb interaction. Right? So for parallel spin, I will have a different result. So P R1 R2, I will first have half of mod phi 1 square 1, mod phi 2 star 2, coming from T1 T1 and T2 T2, where only phi 1 and phi 2 will be interchanged, but basically they will remain the density. But then the minus star, that will be interesting. That will have a phi 1 star 1. So it is not going to become phi 1 star mod phi 1 star. So phi 1 star 1, phi 2 1. Then it will have phi 2 star 1, 2, phi 1 2. And vice versa. You can keep changing. Okay, so that is what led me to this exchange star. Yeah, here. So phi 1 star 1, phi 2 1, phi 2 star 2, phi 2 1, phi 1 2. So here there is no density. That is the point. So that is what I just wrote. So phi 1 star 1, instead of phi 1, it is phi 2 1. Phi 2 star 2, instead of phi 2 2, it is phi 1 2. And vice versa. You write another term. So these two terms have no sense of density. So they are called the Coulomb term. Is it clear? Hello?
Yes, sir.
Yes. Now the very, very important part. If I now make R1 equal to R2, that means coordinate of the space coordinate 1 and 2 are also same. Please look at it very, very carefully. And analyze the case of the parallel spin. What happens to P R1 R1? Can you quickly tell me? Look at this. R1 and R2 are same. So this, look at this term. This becomes phi 1 star 1, phi 1 1. Phi 2 star 2, phi 2 1. Phi 2 2. They're same. 1 and 2 are same actually. So this 1 and 2 are all same. All of them are simply mod phi 1 square, mod phi 2 square. R1
Zero,
R2
sir.
they will become 0. So this Coulomb and exchange will cancel and this will become 0. Whereas for anti-parallel, the P R1 R2 will not become 0. It's a very fundamental point of chemistry of two electrons. So please try to understand this very, very carefully. So what does this mean? This means for a determinant or one determinant, I'm calling it single determinant. Because I have not analyzed any other wave function. I have only analyzed a determinant. Of course, it is a valid wave function, but I told you I could have a valid wave function with two determinants, sum of two determinants. But if I take only one determinant, what I learned is the following, that the probability of two particles or probability density of two particles at same R vanishes if the electrons, okay, when I call particles, I think you can replace this by electrons. I'm talking specifically of electrons, not bosons. It has to be electrons. If the electrons have the same spin, is it clear? If the electrons have the same spin, their probability of coming at the same point is 0. Density. And I have actually formally proved it now. In a simple way, people analyze this, but that is not exactly correct, is that when the two electrons come in the same space, the chemistry people will say they are in the same orbital. Right? So both of them are, let's say, helium atom, both of them are 1s orbital. And of course, then we know they cannot have a parallel spin. right? So in some way, you are actually finding this, that the density of the two electrons vanishes. So if you look at 1s orbital as one point, which is the wrong way to look at it, but within 1s orbital, they cannot come at the same point, the density. But we know that is not even possible because of Pauli principle. But what I'm trying to tell that if you have a 1s and a 2s, both of them have an extension, right? So there's an overlapping region. At same point, a 1s orbital with alpha spin, a 2s orbital with alpha spin cannot come. But if either in 1s orbital or 1s2 orbital, they have anti-parallel spin, then the probability is not zero, which means they can come. And that's a very, they can survive at the same point. Sorry, this is R1, R2, R1, R1. Sorry, this is R1, R1. So probability of the two electrons being in the same point is zero for parallel spins. For anti-parallel spin, it is not zero. And that's a very fundamental point. We will see that we are only talking of probability. There is a similar argument in terms of energy, and we will see this will actually lead to what is called the Hund's rule. That for parallel spin, in the Hund's rule, we'll see why this parallel spin probability density becomes zero, because there is a Coulomb and the exchange effects, which cancelled in this case. For energy, we will see that if there are parallel spin, there is a Coulomb energy minus exchange energy. And because exchange energy is positive and comes with a minus sign, that stabilizes. We will see that later when we come to energy. And that is the reason, given a choice of the same orbitals, electrons tend to be parallel and not anti-parallel. In fact, that is a very important point. We will come to that in the energy. But right now, I have not discussed the energy, how to calculate energy, so forget about it. Right now, we are saying the probability density of the two electrons coming at the same point is zero for parallel spin, non-zero for anti-parallel spin. Is it clear? In fact, it can be shown that the psi of R1 itself goes to zero for parallel spin, and psi of R1 does not go to zero for anti-parallel spin. Again, when I say R1, it's a parallel spin, so I can write alpha, and this I can write, so alpha 1, this I can write alpha 1, beta 1. So, I mean, I'm just doing the discussion for the sake of it, that the probability is zero, probability not zero. If you look at the actual Schrodinger equation, H psi equal to E psi, we can imagine what will happen. So let's say I write this for the two electron problem. Analyze what will happen to H of R1, R2. Remember, there is no spin in the Hamiltonian, so I'm not explicitly discussing spin. But what will be the Hamiltonian for R1 equal to R2? Note again, all this discussion when I'm writing R1, I have forgotten to put the vector sign. But remember, these are vectors. Huh? I'm sorry about that. So please correct it. When I send you the slide, I will correct it. Everything is a vectorial sign, because I'm talking of R1 means it's a space, three-dimensional space. I hope that's clear to all of you. But I just thought I will mention this. There is a small error. But just because I want to be consistent with the notation. So they're all vectors. Okay. So similarly, what I'm trying to say, that at the Hamiltonian at R1 equal to R2, what is the value of the Hamiltonian? Can somebody think of? What is the limit of a two-particle Hamiltonian, in real two-electron Hamiltonian? Don't think of non-interacting. Because these determinants I'm going to use also for interacting problems. So that is why the discussion comes up. For non-interacting problem, it is unimportant. Because it's really just a Coulomb effect, not the exchange will anyway be zero. So in this case, if you see the Hamiltonian, we have a one particle part, but very importantly, we have a 1 by R1 modulus R1 minus R2. So that will become infinity, right? So this is one term in atomic unit. That will go to infinity. Is it clear? So as the two coordinates become same, the Hamiltonian will become singular. So I can say it will become singular. Is it clear to all of you? Because if you remember, my Hamiltonian of a two particle has some h of 1 plus h of 2. And then I told you in the last class, this is 1 by modulus R1 minus R2 in atomic units. And this is the kinetic energy, any external potential, electron-nuclear attraction. And this is just the two particle interaction. And this is not decomposed into sum of one particle Hamiltonian. Hence, this cannot be solved exactly, if you remember our discussion, right? But the point is, if R1 is equal to R2, this part becomes infinity. Is it clear to all of you? So this Hamiltonian becomes singular. And then what is the solution for the psi? Because if the Hamiltonian is singular, any finite psi will make the energy infinity. So for all finite energy, which is what we measure, the psi of R1 tends to 0. That's the only possibility. Because the Hamiltonian is singular. So unless psi is 0, the energy will become infinity. So this is a fundamental point, regardless, and this is important, regardless of the spin. Because when I look at the Schrodinger equation, that I'm looking at a Schrodinger equation where spins are not there. And clearly it has nothing to do with spin, because the Hamiltonian is singular. Hamiltonian does not have a spin at this point of time. So the wave function, it doesn't matter, whatever the spins of the two electrons. To have a finite energy, the entire wave function must be 0. Or in terms of spin, I can say x1 must be 0 for the wave function, because R and R have to be same. So regardless of spin, the wave function must be 0. And because the wave function must be 0, the probability of anything must go to 0. Right? This is an exact case. So this is the Schrodinger equation that I am discussing for the exact case. This is what it should be. So I have reached an important conclusion that for a determinant, or I would say single determinant, to be more precise, wave function, the probability tending to 0 is achieved only for parallel spins and not for antiparallel spin. This was achieved because of the exchange effect. If you remember, they cancelled. Here there is no exchange effect, so the Coulomb term remained. But in actual practice, wave function goes to 0, so the probability should always be 0. So the fact that for antiparallel spins, I got my probability R1, R2 as simply half of modulus phi 1 square 1, modulus phi 2 square 2, so this is R1 and R2 now, plus modulus phi 1 square 2, modulus phi 2 square 1 is not correct. In the exact limit. Because in the exact case, psi must be always 0. So obviously, the fact that this happens for only single determinant is something that you should not forget. I have written for a single determinantal case, it is not achieved. So obviously, the fact that this is not correct is due to the determinant or single determinant approximation. So obviously, there's an approximation. I told you that for an interacting Hamiltonian, why is it happening? Because I have this part. And if this part is there, I have told you one determinant I cannot find to be an exact wave function. What will be the nature of the exact wave function? I will see later. So obviously it is happening because of that approximation. So that approximation that I tended to ignore has a very serious effect on the probability for anti-parallel spins. For parallel spin, somehow that qualitatively, at least the probability is coming to zero. I mean, there would be errors, but for anti-parallel spin, it seems that even a qualitative probability is not coming, qualitatively not coming right. Because the wave function actually should be zero. Two electrons can never be in the same space, regardless of the spin. Many people would think for the power, why it is happening? Please try to understand. In single determinant, you have only Pauli principle, which says the two electrons cannot be in the same space with same spin. Right? That's what you think qualitatively. It's a very qualitative understanding of Pauli principle. And we call this space as the orbital then in some way. But this is the Pauli principle, which is a very fundamental principle, antisymmetry. The problem is this is right, because this space is not actually space, it is orbital. What we are looking at is the probability at a particular R1 with a one determinant approximation. So the problem is not in the Pauli principle. The problem is use of only a single determinant. Because we know that a single determinant will be exact only for non-interacting case. So this brings us to a point, while Pauli principle is always valid, or antisymmetry is always valid, a single determinant, and this I will actually explain even more in the following classes, that a single determinant cannot be, and this is the problem of quantum chemistry that I have referred, cannot be an exact solution for the interacting Hamiltonian. It is okay for a non-interacting Hamiltonian. And for a non-interacting Hamiltonian, this problem is not there. Because in non-interacting Hamiltonian, this term does not exist. So the argument that at R1 tending to R2, this becomes singular, does not exist. This exists only for the interacting Hamiltonian. And for the interacting Hamiltonian, I have been saying that while Pauli principle is valid, while antisymmetry is valid, a single determinant cannot be an exact solution. And I have told you a case where there can be sum of two determinants, which is still antisymmetric, is a solution. So obviously, we have to look for such solution. I'm already giving you hints. We have to look for a solution which goes beyond single determinant. And that is the crux of the problem. Why this is happening. So the fact that for antiparallel spins, P of R1 is not equal to 0 is due to, this is what I'm now writing, due to the use of a single determinant. Approximation for our case of an interacting Hamiltonian. Okay, so it's very important to realize this thing. The fact that this is not zero, PR1R1 is not zero for the anti-parallel spin. So I should write this, not zero for anti-parallel spins. I mean, that's, I hope it is clear, is due to the fact that we are using a single determinant approximation for an interacting Hamiltonian. That is something I can conclude at this point of time. And it's an approximation because it's an interacting Hamiltonian. And this approximation has this problem that the probability of two electrons being in the same space is not zero for the anti-parallel spins. For the parallel spins, qualitatively, there is no problem. Remember, this does not clash with Pauli principle. The Pauli principles did not tell you that use single determinant. Pauli principle simply said that the wave function is antisymmetric. So there are many other ways of making it antisymmetric, of course. A single determinant is an option, was an option to you, but now we understand using it for an interacting Hamiltonian is not a good option. Is it clear? I hope each point is very clear, because otherwise it becomes a confusion.
Sir, can you please explain about the single determinant?
Yes, single determinant is when I write wave function as only one determinant. Let's say chi chi j. One determinant. That is called single determinant. I mean, I have not written 1 by square root 2, all that. It's a determinant, okay?
Okay, sir.
But if I use this plus, I told you, chi k chi l, C2, then it's going beyond single determinant. I've used two determinants for the same wave function. But then you will argue, where is the chemistry? You lost the chemistry here. And that's the problem of normal chemistry argument versus accurate quantum chemistry. Yes, for chemistry, you would like only one determinant. You can say the two electrons are in chi I and chi j. How can I say, oh, two electrons maybe chi I, chi j, maybe chi k, chi l, with some probability, right? But that is what it is. So when we say as a chemist that the helium atom has two electrons, one of them is 1s, another is 1s with alpha and beta, this is an approximation. Unfortunately, entire atomic structure, entire molecular structure, MO diagram are built on single determinant. And each of these is an approximation. So that is where a very rigorous quantum chemistry will always have a problem with the standard chemistry interpretation. I hope you are getting my point. I mean, some of the statements can be shocking to you because you are fed that. If you talk nitrogen molecular orbital diagram, you just write down one by one. I have 14 electrons, I have 14 spin orbitals, right? Which are 7 orbitals, alpha and beta. But it's an approximation. That is what I'm trying to tell you. And that approximation has this problem, that qualitatively, anti-parallel spins are not done correctly. Parallel spins are done correctly, still, qualitatively. So I first did the mathematics. I did not make the statement. I first showed you the mathematics of a single determinant. And now I'm making a statement which may be a little bit shocking. So I'm saying the antisymmetry is, of course, very important. And antisymmetry is the fundamental point, not just important. This is very, very basic for the electron. A determinant is antisymmetric. However, it does not mean that a determinant, A means a single determinant, is an exact solution. Please understand this. And because these two may confuse you. I'm saying antisymmetry is very fundamental. Any single determinant is antisymmetric. However, it does not mean that a single determinant is an exact solution. Because I can have an antisymmetric solution using more than a single determinant. In fact, I can do something else also. So the fact that a determinant is antisymmetric, it's an option for an antisymmetric wave function. Please understand. It does not mean that that's an exact wave function. It is, however, exact. It is, however, exact for non-interacting problem, where Pauli principle is still valid, where antisymmetry is still valid, non-interacting Hamiltonian. Provided I choose my functions correctly. I think there are many, many loaded statements I have made. And I think it's very important. This is an advanced quantum chemistry course. So we must bring you out of that comfort zone. So please try to understand. And actually, we will come back to this very often. But right now, I have proved it by the fact that the probability of two electrons being at R1, R2, or R1, R1, sorry, is not 0 for antiparallel spin, for 0 for parallel spins, but for exact function, it should be always 0. So for antiparallel spin, there is a problem. And the fact that it is happening for the parallel spins is precisely because of the fact that the Coulomb term cancels the exchange term. So here, the Coulomb term was cancelling the exchange term, right? For R1 equal to R2. So in general, you have at the fact that you have an R1, R2 have an exchange term is very, very important for the parallel spins. So again, this shows the importance of the exchange term. The lack of exchange term for the antiparallel spins is the problem. So the probability of R1, R1, I again repeat, is not 0 for antiparallel spins due to the exchange terms becoming 0. Hence, no cancellation of Coulomb and exchange terms can be, hence no cancellation of Coulomb and exchange terms can be realized for antiparallel spins. For parallel spin, however, the exchange terms are there because of the alpha, alpha, all are alphas, so they'll be all there, all are beta, identical. Hence, exchange terms survive, and that exchange terms at this region, when R1 equal to R2, cancel, not always, but when R1 equal to R2, it cancels the Coulomb term. So it's a very subtle effect. So the exchange is required to cancel for the parallel spins at R1 equal to R2. Of course, if R1 is not equal to R2, then you don't realize that the results are wrong or right. In this limit, I'm examining the result. Yeah, I will pause here. I have only 10-15 minutes today. I will pause here and ask you questions if you haven't, because this was a rather, I would say it's not very difficult, but something that you are not used to. So you have to just go back and read this. Of course, I will share the slides, but can you now ask any questions if you have? Many, many things I have told, and many, many loaded things are there. So the statements are very, very important. When you look at the recording, please try to understand the statements. And of course, wherever there are small errors, typos and all that, ignore. The vectors and signs are not there in the beginning. Don't become touchy about them. Okay? But But the major important point that I'm trying to tell is this, that a single determinant cannot be an exact solution for an interacting Hamiltonian. And I have shown one aspect of it. There are many, many reasons. One aspect can be realized by the fact that for the antiparallel spins, the probability of two electrons being at R1 is not equal to 0 in a single determinant wave function. And how to calculate probability is a technical matter, so please practice this integration, only partial integration over omega 1, omega 2, and the confusion that you had of the 4 terms, how to manage, is something that is a little bit technical, but please do this. For a 2-particle term, do it. Is very easily doable. So I would say practice problem, I will not give it an assignment, practice problem, find out PR1, R2. Okay? For case A, where chi I equal to phi 1 alpha, chi j equal to phi 2 beta, case B, phi I equal to phi 1 alpha, phi j equal to phi 2 alpha. Calculate the probability only for R1, R2. So the idea is to do psi star psi, integrate over only omega 1, omega 2, and take psi as a determinant chi I, chi j. I've written everything. So take psi as a chi I, chi j, which means there are 2 terms in the psi itself. So there are 2 terms here, 2 terms here. Don't confuse. Each term has space and spin parts. So when I do multiplication, there will be 2 space parts, 2 spin parts, and 4 such terms. Okay? So this is the only confusion, because you have a determinant here. And a determinant like this, expanded, is a 1 by square root 2 factorial determinant. So I'm not writing that again. It's just these 2 spin orbitals are given, chi I and chi j. So practice calculation of PR1, R2, and then see what happens to PR1, R1. Please see this, that it is 0 for the case B. Sorry, it is 0 for, 0 for the case B and non-zero for the case 1. Case 1 is the antiparallel spin. So this is something that you should practice. This is a technical point. I have done this, I've explained this, but I would always say, if you do your integration on your own at home, you will have a comfort. That is very easy to manipulate star 1, why it is happening. Okay? And you will see that for the case of B, you will have a Coulomb and alpha and exchange kind of term where you cannot tell density. So basically, you will have phi 1 star 1, phi 1 1, phi 2 star 2 after integration, phi 2 2. These are the typical Coulomb terms, and plus exchange, plus 1 and 2 interchange, I would say. But you will also have an exchange term, which is very difficult to interpret. So phi 1 star 1, phi 2 1, phi 1 star 2, phi 1 star 1, phi 2 1, phi 1 star 2, phi 2 2. Yeah. So this has no interpretation, because the 1 exists and another 1 to interchange, minus 1 to interchange. That's okay. That is easy. But electron 1 is in both phi 1 star, phi 2 series, not a density. So that's why I'm calling it exchange. But this is a density. Density of phi 1 interacting with density of phi 2, or where 1 is in phi 1, 1 is in phi 2, or 1 is in phi 2, 2 is in phi 1. It doesn't matter. 1 is in phi 1, 2 is in phi 2, or vice versa. So I think practice this as a mathematical problem, but the final message that I have given from here is very, very important. And that you should remember. Okay, and what happens for the non-interacting Hamiltonian? Because the Hamiltonian itself doesn't have that 1 by modulus R1 minus R2 in that case. So there is no problem. It's only Coulomb. Okay. Coulomb and the exchange comes in a very normal manner. 1 here, 2 here. So that's completely different. All right. So Yeah, if there are any questions, you can ask me. Otherwise, I'll stop today because there is a long class. But in a way, it was good. I will take the Thursday's class, and then from Friday, Professor Sangita Sen will do. So, Sangita, I think, can you suggest me what I should finish before and what you will take charge? Because there are so many things. I can go in any order, you tell me. See, I'm going in something in my mind, but so I just wanted to discuss because on the Thursday, then I will concentrate on that. Do you want me to, so Slater rule, you will do it, right? I mean,
Yeah, Slater rule will take some time. I think you will not
I
manage
will
in
not be
one
able to
class.
do this. So I will probably do some 2-electron problem. I will probably show them that the 2-electron problem, the space and spin part can be separated.
Okay. So
That is, if I take a 2-electron determinant, then if I take a determinant, I can separate the space and spin part, and by one determinant or by combination of two determinants, which will actually
so the
bring them
spin
to
adaptation, little bit of spin adaptation.
singlet and triplet. That I can show.
Okay, fine, no problem, no problem. Then I
So
will start with the integrals and evaluation and all that.
So you will start with
body
the
operator,
Hamiltonian matrix elements.
Matrix elements of the Hamiltonian, Slater rule.
Actually, at that point of time, you can bring in this concept very easily because this will also apply to the energy. So, for example, if you have just 2 electrons stuck here, you have only H part and the Coulomb part. There is no exchange because the antiparallel. If you have this and this, you have both Coulomb and exchange.
Then there is.
I mean, after integration, you can easily show them. So then you can
difference in energy.
Yeah, relate what I've done here. That this is Coulomb and exchange. This is only Coulomb.
Okay.
You will see in Zabosler it is there. Since I will not be there, I'm just telling you, this part would be related. Zabosler actually has this exercise.
Yes, I have seen it. Yeah.
After spin integration in terms of special orbitals, what survives? So they quickly write that if it is 1, H or 2 into H11 plus J11, and so on. Here it is 1 and 2, H11 plus H22 plus J12 minus K12. Right? It is antiparallel.
So one will K12
I think you will be able to relate this with this. All right. So I think
fine. No problem.
Tomorrow. So then we will see. Because it is little bit difficult because I'm not taking the full course. So every time I take the full course, I go in my own way. And anyway, and eventually also Hartree-Fock and all that. At some point of time, of course, I will come back. So I will discuss with you.
Yeah, sure. I will do Slater rule, then I will do Hartree-Fock. And after that, maybe, I don't know, maybe perturbation, you can come back if you like.
So no, but before that, you have to do variation method.
Yeah, variation, of course, before Hartree-Fock. Yeah.
So that is another option that we have, that I can do the variation method. Just do the variation method on one class. With some,
that is also possible.
Not the linear variation, but at least this normal variation. Linear variation will come only later in CI. So you can take up from there. I'm sorry for the students, we are doing a kind of conversation which is about the course, of course, but it is important. So that's, I can just do the normal variation, Euler variation, upper bound, and stop there.
That is also fine. If you stop there, then I will.
So that is
okay. Then I have to go back a little bit to the matrix elements, and then I can again come back.
But also you should
to the application of variation.
No, this 2-electron problem, how to do spin adaptation.
The spin adaptation. I will follow more Szabo and Oslund also. So we will together cover most of the things.
Hello, sir.
Okay, all right. Yes, please.
Sir, I have one question. In the antisymmetric elements, if I do with
wave function,
Coulomb expectation value, the Coulomb term 1 by r prime expectation value of this with antisymmetric element,
wave function.
That should be 0 or not. For both cases, Coulomb interaction.
No, it will not be 0. You will see. That's what she will do. We have not discussed the matrix element yet of the Hamiltonian.
Okay.
But you will see that if I have a parallel spin, and that is what I was discussing with her, if I have a parallel spin only, that means a determinant with parallel spins, wherever there are parallel spin, between those two space orbitals, there will be both Coulomb and exchange, as I discussed here. Energy, Coulomb, that time Coulomb energy and exchange energy. If it is anti-parallel, only Coulomb will be there. You understand? So I think that is a very important part that will come up. So exchange energy will survive only when there is spins are parallel. But it will not be 0, 1 by r minus r prime. Of course, if r is equal to r prime, then as I said, the wave function itself will become 0. I think that is your question, I think. You wanted to find out what happens when r equal to r prime, right? 1 by r minus r prime energy. Is that what you are asking?
Contribution for exchange and the Coulomb term,
So,
that is, I just find out the expectation value of the
expectation value of the Hamiltonian or 2 electron part when you find out with the antisymmetric wave function. The exchange term will survive, exchange energy will come when the electrons have parallel spin. If they're anti-parallel spin, exchange term will not come between those two orbitals. You will see that. So I think just wait for the Slater rules to be done first. So you will be able to connect. And if r is equal to r prime, the question doesn't arise because the wave function itself is 0.
Oh, okay.
So only when the wave function is non-zero, you will actually do this. And in that case, you will see there is an exchange effect for parallel spins, and for anti-parallel spin, there is no exchange effect. So that will be obvious when the energy is done. Right now, we have not done energy. Remember, I am only writing wave function. I have only calculated the probability density. Is it okay? Hello? Yeah.
Okay, sir.
Yeah. What is your name?
Coulomb.
Okay. Yeah, I think you have been asking question. I'd like to hear from others also. Any other question for anybody else? There are 7 of you, so it's all right. If there are no more questions, that's what we'll do. I'll come back on Thursday. Thursday the class is at 10 to 11, and I'll still have one more discussion with Professor Sen on what I'm going to do on Thursday because there will be a change. So I wanted to discuss with her so that there is no jerk. Okay. All right. And I will of course come back later again for 2 to 3 weeks of discussion. Okay. So maybe after the Hartley Fock is done, I can come back. All right. So we will leave there. Thank you very much. We'll meet on Thursday at 10 o'clock. Bye. Okay, bye.